We're going to talk about the geometry of systems of differential equations. First, let's review some ideas from before about modeling using systems of differential equations. Let's say that we have two populations. One we're going to call predators and the other we're going to call prey. For example, we'll consider the running example of foxes catching rabbits. The American biophysicist Alfred Lotka and independently the Italian physicist Vito Volterra were interested in populations and came up with a system of equations that models these two competing populations. Let's denote f of t as the size of the population of predators at time t, and r of t denote the size of the population of the prey at time t. Here, intuitively, f stands for fox, where r stands for rabbits. In order to model these two populations, we're going to make a few assumptions. First, as with exponential growth, we'll assume that the rate of change of each population is proportional to its size. Second, in order to model how the size of the prey population grow, let's assume that there's some number n sub f that depends upon the predators f, such that if the number of predators is greater than this number n sub f, then the prey are hunted and their population decreases. However, if f is small compared to this number n sub f, then the predators cannot effectively hunt the prey, and hence the size of the prey increases. Similarly, let's assume that there's some number n sub r that depends upon the predators, that depends upon the prey, such that if the number of prey r is greater than n sub r, then the prey are numerous, and the size of the population of the predators increases. However, if the size of the prey r is less than this n sub r, then the prey are hard to find, and hence the population of the predators decreases. In other words, we have a system of equations that looks as follows. There should be some constant of proportionality alpha and another constant of proportionality gamma, such that dr dt equals alpha times 1 minus f over n sub f times r. Similarly, df dt equals gamma times r over n sub r minus 1 times f. We'll express n sub r and n sub f in terms of ratios gamma over delta and alpha over beta, so that we can write our predator-prey model in terms of dr dt equals alpha times r minus beta times r times f, and df dt equals negative gamma times f plus delta times r times f. Today we're going to spend some more time discussing the solutions of such a model, but you can see a couple of graphs of the solutions on your screen. We can modify this model a little bit by assuming that there is a carrying capacity for the prey. That is, in general, we know that the number of rabbits cannot increase indefinitely because there's only a finite amount of resources, that is, food and even land space. So let's assume that there's some carrying capacity N. We'll have a model where we can weight the predator-prey model along with the logistic growth model. Simply put, we then have a new equation that states dr dt equals alpha times 1 minus r over n times r minus beta times r times f, and df dt equals negative gamma times f plus delta times r times f. We'll call this the logistic predator-prey model. Today, we'd like to spend a little bit of time discussing how do we actually solve such a system. First, let's write down some definitions. Say that we have two functions, lowercase f and lowercase g, which are functions of three variables, time, a number x, and another quantity y. A two-dimensional first-order system is a system of first-order differential equations of the form dx dt equals f of t, x, and y, and dy dt equals g of t, x, and y. An initial value problem is the extra condition that x evaluated at t0 equals x naught, while y evaluated at t0 equals y naught. We're going to express this initial value problem as d capital Y dt equals capital F, where capital Y at t0 equals capital Y naught, using the following two-dimensional vectors. Capital Y is x comma y, capital F is lowercase f, comma, lowercase g, and capital Y0 is lowercase x0, comma, lowercase y0. We'll say that a vector valued function capital Y of t is a solution to this initial value problem if capital Y of t equals lowercase x of t, comma, lowercase y of t, where lowercase x and lowercase y are functions that satisfy the equations you see on your screen. We'll say that our system of differential equations is autonomous if lowercase x and lowercase g are independent of the time t. Given an autonomous system, we'll say that capital Y sub 0 as a vector is an equilibrium point if capital F evaluated at capital Y sub 0 equals the 0 vector. That is, capital Y sub 0 equals x naught comma y naught, where f evaluated at x naught comma y naught equals 0, and lowercase g evaluated at x naught comma y naught equals 0. A constant function, capital Y evaluated at t, equals capital Y sub 0 is an equilibrium solution if capital Y sub 0 is an equilibrium point. Let's review some examples. First, I claim that the predator-prey model has exactly two equilibrium points. You can see them here on your screen in terms of the coefficients for the model. That is, if we have dxdt equals alpha times x minus beta times x times y, and dy dt equals negative gamma times y plus delta times x times y, then the two equilibrium points are 0, 0, the origin, and n sub x, comma n sub y, where n sub x is gamma over delta, excuse me, and n sub y is alpha over beta. To see y, let's denote the functions lowercase f of xy as x times alpha minus beta times y, and g of x equals y times negative gamma plus delta times x. We want to set both x of f and g equal to 0 simultaneously, and then solve for x and y. We factored these functions lowercase f and lowercase g so that we can find solutions as follows. For lowercase f, let's set x equal to 0. Then, to set g equal to 0, we find that we must have y equals 0. On the other hand, let's say that alpha minus beta times y equals 0 for f. Then this means that y equals n sub y. That is, it equals alpha over beta. Substituting this into the second equation for g, we then find that x must equal gamma over delta. That is, x equals n sub x. Hence, these are the only two times which we can simultaneously set f and g equal to 0. Let's consider now the logistic predator-prey model. This is slightly more general than what we had earlier in today's lesson, but still you can see the constants and the coefficients on your screen. I claim that there are exactly 4 equilibrium points for this initial value problem. Let's explain why. First, let's express lowercase f and lowercase g by factoring out x and y from f and g respectively. If we want to set f and g equal to 0 simultaneously, we have a few cases to consider. For f, first let's say what if x equals 0. If we plug this into the expression for g, then we find two values for y, namely y equals 0 and y equals m sub y. These are 2 points. Similarly, for g, what if y equals 0? If we plug this into the expression in f, then we find that there are two values for x, namely x equals 0 and x equals m sub x. So these are 2 points now for capital Y0 for our equilibrium. Finally, what if neither x nor y equals 0? Then by looking at the factors for f and g, we then have 2 equations and 2 unknowns. And we can solve for x and y to find the rather cumbersome expressions you see on your screen. That is, x equals n sub x and y equals n sub y. Hence, there are 4 equilibrium points in general for the logistic predator-prey model. Let's go back and consider a general autonomous two-dimensional system. We'd like to make a few more definitions. A slope field is a plot where, given a point x comma y, we can place an arrow at this point in the direction f of x comma y, comma g of x comma y. Given an initial point x0, y0, we simply follow the arrows in order to plot out a solution x of t, comma y of t. An equilibrium point is a point x naught, y naught, where the arrow f of x naught, comma, y naught, g of x naught, comma, y naught equals the origin. That is, this arrow is trivial. Let's now discuss a few examples of these concepts. Let's start with the autonomous system dx dt equals y and dy dt equals negative x. On the upper left part of your screen, you can see where we've plotted out a pair of solutions. The blue is x of t, and the gold is y of t. We'll discuss in a later lesson how to actually find these solutions numerically, but let's just accept this for now. On the upper right-hand part of your screen, you now see the slope field. You'll notice that we have a black circle, which represents the solution. The brown dot is the initial point, and you can see that as this brown dot follows the arrows in the slope field, this will move around in a circular pattern, and we find periodic behavior. On the other hand, take a look at the blue dot in the middle of this slope field. This is where the arrows all are 0. This is exactly what it means to be an equilibrium point. This point is stationary, and it doesn't move with respect to time. Let's consider another equation corresponding to the predator-prey model. In this equation, you can see that we've actually tried to plot out solutions. Will be the plots that you see on the left-hand part of your screen. The blue represents r of t. This will be the rabbits as a function of time. And the gold plots f of t. This will be the foxes as a function of time. On the right-hand part of your screen, you can see that we've plotted out the slope field. The brown dot would be an initial point, and the black curve would now be the solution. Let's be a little bit careful here because we're plotting r on one axis, the number of rabbits, and f on the other axis, the number of foxes. You can see that this really does represent the periodic behavior that we found before. As the number of rabbits increases, that is, the arrows try to move us from left to right, we then see that the number of foxes must increase. This is where the arrows now pull the curve upwards, but as the number of foxes increases, they start to eat the rabbits, and the number of rabbits decreases. This is now the arrows moving slightly from right to left. But now, as the number of rabbits decreases, this means that the number of foxes must decrease. Hence, the arrows start to move from top to bottom. This explains the periodic nature of the predator-prey model. You can also see that there are two equilibria points in this case. The blue dots represent these 2 points. One of the points is at the origin, 0, 0, and the other one is slightly in the middle of the graph at 1.11, 1.67. Finally, let's consider some examples of the logistic predator-prey model. Here you can see on your left some examples of solutions as we take a look at initial conditions. On the right-hand part of your screen, you can see a solution where we started with a brown dot and we've moved through the arrows, but this curve now is no longer periodic. What's happening here is that the solution, that is the black curve, spirals inwards towards one of the blue dots. The blue dots, of course, are one of the 3 equilibria points. In this case, it spirals in towards the point 1.11, comma 0.47. But now let's take a look at what happens if we had a different initial condition. Maybe now the brown dot is over to the right-hand part of your screen. You can see here that the arrows still carry this black curve and spiral in towards one of the blue dots, the equilibrium point at 1.11, comma 0.74. Let's consider one last starting point. Now let's take a look at this brown dot that's over towards the left-hand part of the slope field. Again, you can see that the arrows carry along this black curve so that the brown dot spirals in once again towards the equilibrium point, the blue dot, at 1.11, comma 0.74. Thanks very much for watching today.